Hello everyone. So this is the first lecture of third week. What I wanted to do today is not really a lecture, but more to help you walk through the second week's assignment, assuming that you have looked at it and you've made an attempt to solve it and you have also uploaded your solutions. We will see how we will go about solving it. What are the questions? Let's discuss our understanding of structural coverage criteria over graphs to see if we could solve this assignment fully correctly. This lecture assumes that you have gone through all the videos of the graph structural coverage criteria, the algorithms for graph structural coverage criteria, and you've also looked at the assignment for the second week and made an attempt to solve it. So what I'll do now is I'll walk you through one question after the other, tell you what the correct answer is, and tell you how to get the correct answer. So which was the first question? The assignment had 8 questions. The first question talked about coverage criteria subsumption. To read out the question, it asks which of the following depicts a correct order of subsumption amongst the various listed coverage criteria below. So this notion, right, this symbol, right arrow, you should read it as subsumes. So how do I read the first option? Your answer is to choose one of these options, the correct option. How do I read the first option? You read it as prime path coverage, subsumes edge coverage, which in turn subsumes node coverage. Similarly, second one would be node coverage, subsumes edge pair coverage, which in turn subsumes edge coverage, and so on. So the correct choice for this answer, for this question, happens to be the first answer. That is this one. Prime path coverage does subsume edge coverage, which in turn subsumes node coverage. Now, why are the rest of them not the correct option? If you see the second option, it says node coverage subsumes edge pair coverage, which in turn subsumes edge coverage. So it has two subsumption relation like all other options. The second one, edge pair coverage subsuming edge coverage, is correct. But node coverage does not subsume edge pair coverage. So this is not the correct option. Similarly, for the third one, edge coverage does subsume node coverage, but node coverage clearly does not subsume complete path coverage, right? In fact, complete path coverage could even be infeasible, as we discussed several times. So third one also cannot be the right option. What is the fourth one? It says node coverage subsumes complete path coverage, which in turn subsumes prime path coverage. So this part is correct. Complete path coverage does subsume prime path coverage, because if I do complete paths, I always include prime paths in my TR. But this is not correct, as I told you in the option for the previous answer. Node coverage does not subsume complete path coverage. So except for one, the other options 2, 3 and 4, one of the listed subsumptions is not correct. So none of them can be a correct answer. In the first one, both the listed subsumption criteria happen to be correct. So the first one is the correct answer. Now moving on to the second question. Second question was a simple fill in the blank question. It asks the following. It says the requirement of length dash should be added to edge coverage to make it subsume node coverage. The answer is requirement of length up to 1. If you remember what edge coverage is, the test requirement or TR for edge coverage said you cover all the edges of the graph. So all the edges of the graph means all paths of length exactly 1. So I don't keep it as exactly 1, I make it as length up to 1 because I want edge coverage to subsume node coverage. Node coverage TR says nodes are paths of length 0. So if I include the requirement length up to 1, it includes paths of length 0 and it also includes paths of length 1. So because I want edge coverage to subsume node coverage, I change the requirement for edge coverage to be all paths of length up to 1 as its test requirement. So the answer for this would be all paths of length up to 1, right? The next question asks, again a fill in the blank question. It says tours with dash and dash are added to test paths to make infeasible requirements feasible. Right? If you remember the lectures, we had discussed about side trips and detours. Side trip, basically you take a test path and then at some point in a vertex in a test path, you decide to move out, take another small side trip, come back and join the vertex, right? What would be a detour? Detour is very similar to a side trip, but it might skip some edges also on the side trip. Why would I need this? If you remember, test paths, especially those dealing with prime path coverage, could sometimes become infeasible. The test requirements will become infeasible, especially if I have a loop like do while loop and I look for prime path coverage on that do while loop. I may not be able to skip the loop at all, right? Because do while says you first do one execution of the loop and then you check for the condition, whereas prime path coverage will insist on skipping the loop. So I say I meet that test requirement for prime path coverage by using a test path that will skip the loop but actually execute the loop as a side trip, right? So they're very useful to make infeasible test paths as feasible. So the next question was again fill in the blank question. It asks what sort of a path a prime path is. A prime path, if you remember the definition, is a simple path that doesn't come as a subpath of any other path. So prime paths are what are called maximal simple paths, maximal length simple paths. Why do I put maximal and not maximum? I hope you know the difference. Maximal says that there could be more than one maximum length simple paths, right? There could, if you see the example, if you remember that we looked at while dealing with algorithms for structural coverage criteria, there were prime paths of length 2, there were prime paths of length 3, and there were prime paths of length 4. For each of these lengths, that happens to be the maximum length simple path. So that's why we say maximal. So the answer to this is a prime path is a maximal length simple path. The last 3 questions in the assignment were to deal with coverage criteria that is based on an example graph that was given as a part of the assignment to you. So here is the graph. So the graph had 7 vertices numbered 1 to 7. The vertex 1 was the initial vertex or the start vertex. The vertex 7 was the only final vertex, and these were all the edges in the graph. And then you had 3 questions, 5, 6 and 7, which dealt with answering questions about coverage criteria on this graph. So before we go ahead and look at how to answer the questions 5, 6 and 7, whenever I'm asked a question like this, the first wise thing to do is to be able to draw the graph, to be able to visualize the graph for yourself. What are the benefits of drawing the graph? One is the notion of how the edges are placed, what the edges are, and how to look for paths in the graph becomes visual, and it becomes a little more clear, right? Than instead of staring at this set repeatedly to figure out what the notion of paths is. And things like how to achieve node coverage, how to achieve edge coverage, even to the extent of how to achieve prime paths coverage can be looked at the visual graph and answered very easily, intuitively. You don't even have to use the algorithms that we discussed to be able to come up with test requirements and test paths for these criteria. So that's what I've done for you now. I have drawn this graph. So this graph has 7 vertices, 1, 2, 3 and so on up to 7. So I have put these 7 vertices. Another thing to note is that while drawing the graph, you may not get the layout of the graph so perfectly fine. Don't worry about that if you have to draw long edges, short edges, skewed edges. It still helps to have a visual graph. And then I've marked this initial vertex 1, marked the final vertex 7 using double circles, and then I have marked the edges. If you see, there were so many edges, about 9 edges. So there were 2 edges going out of 1 to 2 and 1 to 7. I've marked those edges, 1 to 2, 1 to 7. 2 edges going out to 2, 2 to 3, 2 to 4. Marked here, 2 to 3, 2 to 4. Only 1 edge going out of 3, which is from 3 to 2, 3 to 2. 2 edges going out of 4, 1 to 5, 1 to 6, so 4 to 5, 4 to 6. 1 edge going out of 5 to 6 and 1 edge going from 6 to 1. So here is 1 edge going from 5 to 6, 1 edge going from 6 to 1. So I think we've captured all the edges here. So this is the graph that is the same as this but drawn. So now let's go ahead and look at the questions that were asked about this graph. So question number 5 says, to list all the test paths that satisfy node coverage, but it also says that some of list test paths in such a way that they satisfy node coverage but do not meet edge coverage. If you remember, node coverage does not subsume edge coverage in all cases. So in this particular graph, node coverage need not subsume edge coverage. So it might be possible to come up with a set of test paths that satisfy node coverage but not edge coverage. So what is node coverage test requirement for this graph? It is basically the set consisting of all the 7 vertices. What are the test paths for node coverage? If you see, this path from 1 to 7 is like a loner path, right? It's on its own. So you have to be able to take this. This is the only way to go to 7. So to do node coverage for the vertex 7, I need to be able to include this as a standalone test path. It is a test path because it satisfies all the requirements of a test path. It begins at an initial vertex, which is 1. It ends in the final vertex, which is 7. So I have to be able to include this test path to node cover 7. So the remaining nodes are 2, 3, 4, 5 and 6. So how do I cover them? I can include any test path. Remember, test paths always have to begin in an initial vertex and end in a final vertex. So I begin at 1. I don't have much of a choice here. I go to 2. From 2, let's say I go to 4, 5, 6. From 6, I go to 1. So which are the nodes I have covered if I had taken such a path? I have covered 1, 2, 4, 5, 6. Earlier I had covered 1 and 7. I have left out 3, right? But I am still not left out. So I can always go back and then I'll continue this path. I'll take it from 1 to 2. I visit 2 once again. That's all right. There's no harm in that because test paths can have cycles. And then I go to 3. So I have covered now all the vertices, but I can't end my test path here because a test path has to end in a final vertex. So I take this vertex back and now I still can't go to 7. The only way to go to 7 is to go to 4 and then maybe do this 4 to 6, 6 to 1 and 1 to 7. So basically what I'm trying to say is that if my test requirement is node coverage, then there has to be a test path that consists of this segment in the graph, which is just this edge 1 to 7. And for all the remaining vertices, you need to go through this whole zigzag cycle once and come back to 7. You could include any test path that does that. Here, what I have done is I have included this test path. I have done 1, 2, 3, 2, 4, 5, 6, 1, 7. So to trace it out, 1, 2, 3, 2, 4, 5, 6, 1, 7. It does meet node coverage. If you see, all the nodes are included in this test path. But I had one more condition in my question, that was don't make it subsume edge coverage. So I have chosen test path in such a way that I have left out one edge, which is this edge. I have left out the edge 4, 6. So if you see, this test path achieves node coverage, but it almost achieves edge coverage. It visits all the edges except for this edge 4, 6. So this test path is good enough an answer for this question. So the next question says, list all the test paths that can satisfy edge coverage criteria on the graph. So here there could be several possible correct answers. In fact, 4 different possible correct answers are there. Let's go back and look at the graph. As I told you, right, this path is a standalone path. It always has to be taken, whether you do node coverage, edge coverage, prime path coverage. So 1, 7 will always be there. If you see in all the 4 options that I have listed here, 1, 7 is always there. And then there's a question of this covering the rest of the edges. So if you see, when I execute, the only thing to remember is that all these are pretty much serial. It's only at this place do I have a branching or a choice. Of course, at 2 also I have a branching, but it's this or this. But once I do that, again I have another choice here at 4. So suppose I take this branch 4 to 5, 5 to 6, then I have left out this one, this edge 4 to 6. So I need to be able to come back. How do I come back? The only way to come back is to go from 6 to 1, 1 to 2, 2 to 3, 3 back to 2, 2 to 4, and then I have to take 4 to 6. So the 4 options basically exploit this. So you have to do 1, 7 separately. And what are these 4 options? They let you traverse from 4 to 6, either using the 2 edges 4 to 5, 5 to 6, or using this single edge 4 to 6. So it says 1, 2, 3, 2. Use the edge 4, 5, 6. Go back to 1 and then to 7. Finish. And then you begin at 1. Go to 2. Use the edge 4 to 6, the direct edge. Do 1 and 7 again. This one is the same thing, but it says, so I'll just trace it out here. You do 1, 2, 3, 4, 5, 6, 1, 7. Or you do 1, 2, 3, 4, 6, 1, 7. The second one, what I have done is I have done 1, 2, 4, 6, 1, 7. And then I have done 1, 2, 3, 2, 4, 5, 6, 1, 7. So those are the two options here. And the last two options, I've basically joined them both. I've avoided this repetition of going back to 7 and beginning again at 1. I just go back to 1 and resume from 2 again. So what I have done, just to trace the path here, is I've done 1, 2, 4, 5, 6, 1, 2, 3, 2, 4, 6, 1, 7. That's this one long test path that's here. The second one reverses this order of visiting, 4, 5, 6 and 4, 6. It does 4, 6 first and then 4, 5, 6. So 4 answers for edge coverage, do 1, 7 separately, and then the rest of these paths, visit them in any order that you like. But you have to be able to do this large, strongly connected component twice. Once going through this path and once going through this path. And there is a choice here similarly at 2. Once if you exercise this, then the next time you have to be able to exercise this. That's the only way I can cover all the edges in the graph. So that's the test path for edge coverage. The last question of this assignment asks you to go back to the graph and consider the simple path 3, 2, 4, 5, 6. So let's go and see what that simple path looks like. It's this 3, 2, 4, 5, 6. Please remember, the simple path is not a test path. So it can begin and end at any node. The only thing to note is that it's a simple path. It doesn't have any cycles. So suppose you had a specified path coverage requirement of having to write a test path that covers this simple path. So they have made an attempt, given you a test path. So the test path is fairly long. It does 1, 2, 3, 2. Then does the 4, 6 edge, comes back to 1. And does the 4, 5, 6 edge and comes back to 1 and then to 7. It's this long path that just walks through the entire graph once, round and round. So the question that was asked were two parts. Does this test path tour the simple path directly or with a side trip? The test path doesn't tour the simple path directly, right? If you see, the simple path is 3, 2, 4, 5, 6. It's split into two parts here. 3 and 2 come here. 4 and 5 and 6 come here. So it doesn't tour the simple path directly. If it tours the simple path directly, the simple path will be a contiguous subpath of the test path. Because it's not there, it doesn't tour the simple path directly. So the test path, in fact, tours the simple path with a side trip. So what is the side trip? Side trip is this bit that's left in between. So 4, 6, 1, 2. So you could write it like this, 2, 4, 6, 1. Or you could include 3 and this 2 and make it 3, 4, 6, 1, 2. So this test path towards this given simple path with the side trip, and the side trip looks like this. If you had written either of these, it would be acceptable as a correct answer. So I hope this small exercise helped you to understand how to solve simple assignments that we would be giving every week. I'll try to upload a couple of more videos as we move along for other assignments that will help you to solve these assignments. For now, to get to know more about graph structural coverage criteria, I encourage you to look at the web app that comes as a part of this course book. It's a very nice app. It'll help you to learn how to represent graphs as adjacency lists and how to feed them and how to do various coverage criteria. Please do try it out. Hope it will be useful to you. Thank you.